Thanks a lot, Xenia, for your kind words. And it's a real honor to be here with you today. And I feel I'm pretty nervous. It's a homecoming type of feeling to speak on the Eawag stage. But yeah, I'm glad to be here. And I'd like to thank all of Eawag of Ecotox Center and also the directorates of both institutes for their trust and giving me the opportunity of continuing in this very inspiring and supportive environment. I cherish this a lot and I'm very grateful. And today, I want to take a dive with you into regulatory ecotoxicology and environmental risk assessment. I brought this outline, maybe stand on this side. To start with, I'll give a very brief overview of what I'm currently doing at Ecotox Center, because I think this will also give you an idea of what we do as a center as in general. This is not known to many, I think, guessing from conversations I've had. Then I'll give a very brief introduction to environmental risk assessment to put us sort of on the same page. And then I've brought 3 topics that I thought would be of interest given current also media coverage and topics that we are covering in both Ecotox Center and at Eawag. So let's start with what I am from a scientific point of view at the moment. There's research and consultancy that we are doing. This is part of the Ecotox Center mandate. So we provide information, guidance, consultancy to the offices, the federal offices and the cantons foremost, but also practitioners and the general public in different topics that are listed here, but many more depending on which type of requests we receive. Then we have a bunch of advisory roles. I've listed some that I'm involved in right here. And there's other activities that we do, among others, organization of further education courses for practitioners and the federal offices. We participate in public consultations for the federal ordinances and do quite some media coverage, especially in the past months, due to the topics that we'll touch on today as well. And I put this little picture here, which is part of a stream biofilm, which is sort of my pet that I kept from my days back at Etox, which is very close to my heart. And we are hoping to extend on this or expand on this in the future at Ecotox Center. So regulatory environmental risk assessment is a pretty complicated term. And I put up this little box here. Thanks to Xenia, we'll have a UCAM seminar coming up in June, hosted by Brianne Holmes, our colleague at Ecotox Center, and she'll speak about environmental risk assessment. And today I'll just briefly touch on things, but please do ask if something is very confusing. So what is environmental risk assessment about? Why do we need this? It's about understanding that things, in this case, our friend the shark, can be a hazard, but we are only at risk when we're exposed to it, right? Then you need to swim or do whatever is useful. But with chemicals, this assessment that we do intuitively is much more difficult because oftentimes we have no idea, no information to start with. So what this risk assessment is about is it's a systematic process. It's defined to understand the potential adverse effects in ecosystems and human health. And it has 3 parts, the hazard identification, so this would be the shark, then the exposure, am I with the shark or not? And then you build a risk quotient comparing these 2 items, basically. And in a more figurative way of putting this, you go ahead, in your first step, you establish your effects, which could be growth inhibition due to a herbicide, for example. Then, which is more important, is you try to understand where your hazard threshold is. So when does your effect actually start? When do you start to see it? And of course, all of what we do in science is linked to uncertainty. So when you establish your threshold value, you need to take into account the uncertainty of all your testing and all the assumptions you have made, which we do with safety factors. And then you go ahead and determine your exposure, either by measurements or by modeling, and you end up with your risk quotient, which ideally is below 1 if you compare your actual concentration with your threshold. If it's above 1, you need to go to risk management and see what you can do about it. And we are basically, we stop here. So this is where our responsibility stops. Now, just to go back to history really, really quickly to see how long we sometimes take to take action. So back in the 19th century, we already did fish toxicity testing, and we understood that there is a connection between water quality and effects on fish. So this is way back. But it took us, after mass production of chemicals, it took us incidents and lots of publications like Silent Spring that you all know, that we started introducing environmental law to deal with these. But then looking at EU legislation, it was not till 1985 till the first environmental risk assessment actually became mandatory in the EU. It took till 91 till there was guidance, or there was legal document for plant protection products. And then again, Switzerland followed suit 3 years later when this was implemented in Swiss legislation. And in the next slide, I'll try to summarize which areas today we do risk assessment in where it's legally required. These are these 6 areas of regulation that are identical in Switzerland. Some are part of our national law, and some we are directly linked to the EU law. Now, these 6 different types of regulation fall into 2 different categories. 5 of these, so plant protection, biocides, REACH, so industrial chemicals, human medicines, and veterinary medicines, these are prospective regulations. This means you look at your substance before it enters the market. So you try to understand what risk it can pose given the type of use that you anticipate. Then the water protection law or legislation is a retrospective one. This means it takes everything into account that leads to a substance to enter the environment. And while here you can basically take risk mitigation measures to avoid the emission of a substance on this side, you can only take measures to reduce at the end of the pipe, basically. What's interesting to know is that only for 3 of these, that's marked in green, your risk assessment, it has consequences on the approval or the registration or on your water quality status. For industrial chemicals, veterinary medicines, and human medicines, your risk assessment outcome does not have any effect on your approval or the registration. This is, I think, an important fact. And another point is that all of these are under different regulatory bodies that have different responsibilities. So this is a bit of the background. Despite all of these things that we have established in the past decades, the key challenges remain, which I'm not going to discuss in detail. I just wanted to list them here for you to have an impression. Complex mixtures is at the very top because this is what our environment is right now. This is what we've produced, basically, and we have hundreds of thousands of chemicals we need to deal with. And there are certain types of substances that pose challenges. And 2 of them, we'll see this in a minute, we'll look at a bit in a bit more detail today. I've also put up here NAMs, which is an important topic that hasn't triggered down into regulation that much, and the One Health principle where we link environmental and human assessment. Of the 3 examples I brought today, we touch on substances with high persistency, partially low solubility, and effects at very low concentrations. So let's see what these are. Now, I'll dive into the first topic. This is something that is very close to my heart, I must say, because I think we could do much better. We in a park project, we are analyzing this topic of regulatory silos, as I said, different regulatory bodies being responsible, and delays. You've seen Park in different presentations, I believe, and we are in the famous task 6.3. There's many others where we scrutinize the environmental risk assessments under these different legislations, except human medicines. This is a separate project, which I find is very pitiable. It should be in this project, but it's not for various reasons. Now, there's only legislative links at present on EU and on Swiss level between water protection and plant protection products and biocides. And I'll show you how this works. So in the EU, if the goals of the water protection Water Framework Directive are not met, the approval of substances under these legislations should be reviewed. It's not a must, it's a should. In Switzerland, we do have a feedback loop as of a few years. This year will be the first year when a review will be possible. We'll see how that will work. We don't know yet. But it's important to know that of the over 300 substances that we use, for example, in plant protection, only 10 are in our water protection ordinance. So it's only a small fraction. There's many more pesticides in the water protection ordinance which are not approved any longer. So the lever we have with this feedback loop is rather small. I've brought one example, which is deltamethrin. It's not in the water protection ordinance. Deltamethrin was one of our candidates in the study we did under Park. It's a type 2 pyrethroid. It's also called a second generation pyrethroid. It has this funny Cerner group right here, which makes it very stable. It's been developed in the 20th century, and as of then, it has been used as an insecticide basically worldwide. If you look at the Swiss uses, it's used in plant protection, biocides, and veterinary medicines. We have no idea how much of it is used for the latter two. For plant protection, it's 130 kilograms a year. Doesn't seem a lot, right? We'll look at this in the next slides. I'll try to walk you through this slide. So this is trying to summarize our analysis of what has happened with deltamethrin in the EU and in Switzerland since it entered the market. We remember that the first time there was a mandatory era for plant protection products was in 91, right? And then Switzerland started with this in 94. Before, deltamethrin was used under different national legislations, but not always with a risk assessment. It was just in use. So it was decided that deltamethrin should be assessed in 92, I'm sorry. It took till 98 till the first draft assessment was available. It took to 2002 till on the EU level an environmental risk assessment was agreed on, so 10 years later. I'll go into the numbers here in a bit. It was approved a year later for 10 years. And then, in the meantime, new regulation came into force for PPPs in the EU, and again, Switzerland followed suit 2 years later. It was extended to 2016. In the meantime, the biocide regulatory body had also listed it as having to be assessed, and 8 years later, there was an assessment. Now, let's have a look at the figures here. The 3.2 nanograms per liter is what the authority thought could be in the environment without risks. 3.2 nanograms per liter in the water. Already 9 years later, another authority thought that it should be below 1 nanograms per liter. So this is because different data was used. And now, in 2013, one of the producers published a study with an amphipod that, that already had acute effects below these values that were considered safe in the environment, right? 2013. This went into the ongoing risk assessment on the EU level. But you can see here that the allowed concentration was still above this one. And then in 2023, so 2 years ago, it was accepted that this is the lowest endpoint, basically, but we don't have a new safe concentration for the environment yet, so in 2023. And right now, the entire process is stopped because delta methrin is under ED, endocrine disruption assessment. So we're still on the EU level working with this value, and in Switzerland working with 1.6 nanograms per liter, which is 10 times above what kills 50% of Hyalella azteca. Fortunately, for the Water Framework Directive, we already have a suggested value for water quality safety. This was suggested in Switzerland in 2018. It was taken on by the working group in the EU for a suggestion under the Water Framework Directive. It was proposed for the Water Framework Directive in 2022. And now it has been suggested for approval in the EU. In Switzerland, which you may have seen in the media recently, is currently under discussion. So it's not clear whether this will be taken up into the Water Protection Ordinance or not. So this is our political situation at the moment. And now I'd like to show you the database that we have to assess delta methrin. In this graph, you see the acute data we have and the chronic data for 3 weeks exposure and the micrograms per liter effect concentration. So when does an effect occur in these different organisms? These are fish and crustaceans and algae and what have you. You can see that there's much less data for chronic exposure than for acute, and there's a large spread of data, right? So it really depends on the group of organism. And if you look to the bottom of the acute data, these are small crustaceans, so amphipods, mysids, gammerids, which we don't have chronic data for. So we only know when they die soon. And now, oh, sorry, I forgot to animate this. If you take this value, so 1.7 picogram per liter here, and compare it to actual concentrations in the EU, measured water concentrations, this is 4 countries that are anonymous here that reported delta methrin concentrations. You see that they are well above what could be considered safe under the Water Framework Directive. And this is not only the case in Europe. If you jump to Switzerland, this is data from 2019, where various pyrethroids were measured in Swiss watercourses. You can see here, this is delta methrin, that our concentrations are also well above this recommended concentration. And the blue line indicates where acute effects already occur. So this is our approval situation at the moment. And in the last slide to this topic, I would like to jump to public perception of pesticides. Along with delta methrin, I listed one that you've most probably heard of multiple times in the media, glyphosate, that triggered a large emotional debate with NGOs in politics. And what I compare here is sales data of glyphosate and delta methrin in Switzerland. So there's over 70 tons of glyphosate used or sold every year for plant protection, 0.1 for delta methrin. The safe concentration in water for the glyphosate is 50 micrograms per liter. For delta methrin, currently, this is 0.6 nanogram. If you do a ratio, you see that per ton, basically, the toxicity that you put in the market compared between these two differs a lot. And it differs by a factor of 53. So with delta methrin, we put 53 times more toxicity on the market than with glyphosate. This type of benchmarking is not being done when we approve of substances. This is not being done. It's considered in the PARC project as a suggestion. But yeah. What I take from this is we need to actively communicate with our stakeholders, not in a political manner, not in an activist manner, but to provide the information that's necessary to allow for a balanced public debate. And now I'd like to jump to the next topic. Hope you're still with me, which is, I think, even more complicated in a certain sense, but also very relevant and will be with us for decades to come, which is the PFASs. And I would like to look at the challenge of suggesting water quality standards for PFAS. This is what we work on. Marion and I recently had a project for the Federal Office of the Environment on this. And for me, this is the figurative iceberg, basically. And I always feel absolutely overwhelmed with the complexity of this topic, I must say. I brought a bit of history here as well, because I find it really astonishing. PFAS were accidentally discovered early in the 20th century. And then there came mass production of PFAS after Teflon had already been on the market. But then here in the 1970s, 1970s and 80s, it became evident that this is an issue. So the PFAS that were produced were found in the workers' serum. And there was also evidence of birth defects in the workers' children. Then US EPA already early on, or sort of early on, uttered concerns about PFOA, but it was not till 2000 that 3M phased out PFOS, basically. So how does this story continue? We end here after several restrictions on PFOS and PFOA, and the EQS proposal I'll present today. Till in 2023, at least in the EU, a restriction proposal was put forward. This is still under debate. There's lots of pressure from different stakeholders, and it's not yet finalized. So, we're talking over 85 years till we maybe get a restriction. Just in a nutshell, what are PFAS for those who haven't had so much exposure to it in a data kind of sense, sorry, that was unintended. So it's synthetic compounds. They are organo compounds and they are fluorinated either fully or partially. They have various functional groups, which makes them absolutely diverse, and they have a high persistence in the environment. And going with the OECD list of PFAS, we're talking nearly 5,000 substances, which is already enough, but there are definitions that go to millions of substances. I'll briefly mention TFA, which may ring a bell with one of you or the other. It's trifluoroacetic acid. This is the smallest PFAS by definition that we have, and it's absolutely stable. And it's the degradation product of many PFASs that especially have these functional groups. They'll get oxidized, and in the end you end up with TFA. It's persistent, it's mobile, and it will constantly accumulate in the environment. I brought this slide really briefly for a rule of thumb, what these substances do in the environment. Depending on the chain length, they'd rather be water soluble or persistent in or absorb to soil and organic matter. And this will also facilitate bioaccumulation. Now, with this background, what the main challenges for us are, which you may have guessed from what I introduced, is the complexity of the group, the large group, the diversity of physical chemical properties, which also mean differences in bioaccumulation and excretion, and they are regulated under different frameworks. So you have different types of thresholds in parallel for the same substances, which doesn't help with communication. This is an overview of the legislations PFASs are regulated under. And all of these have different approaches and different protection goals, which leads to different assessment outcomes. And today, I'll focus on 3 of them, which will be water protection, Water Framework Directive, Water Protection Ordinance, then drinking water and foodstuffs. And the foodstuffs directive was a bit in the media in the past weeks and months, because of the restrictions that were necessary in St. Gallen due to the findings of PFASs in foodstuffs. So what was a turning point, sort of, in threshold derivation for PFASs was the decision of EFSA to review their total weekly intake TWI in 2020. A few years before, they had already lowered their threshold, but decided based on scientific evidence they needed to go over the books again, and came up with a value of 4.4 nanograms per kilogram for 4 PFASs that are listed here, assuming equipotency, so assuming all had the same toxicity. And the most sensitive endpoint was immunotoxicity, vaccination response in small children and infants. And this value triggered various revisions, starting with the EU directive for residues and foodstuffs, which was approved in 22 and was then taken over in Swiss law last year, which is why St. Gallen now has these issues. And there's a long list of different foodstuffs that have been regulated. They differentiate between fish species and also age of the consumer. So adults have different thresholds than infants, for example. And I brought the lowest ones, which is 2 to 45 micrograms per kilogram of the sum of these PFASs. That's that. Then the next step was to update the EU Drinking Water Directive. This will be implemented in Switzerland next year. This is already decided. Here, the threshold is for 20 PFASs, 5 times more, and it's 100 nanograms per liter. It's also based off of this value right here. Now we jump to the Water Protection Ordinance, which is different. Sorry, this was a mistake. We now jump to the Water Frame Directive, which is different from the Swiss Water Protection Ordinance. So the Water Protection Ordinance, as up to now, doesn't have any protective values for human health, whereas the Water Frame Directive does. This is why these values here for water, drinking water, and for foodstuffs are to protect human health. This is a novelty, basically, novelty. And what becomes apparent here is that you have a double regulation. So under the drinking water ordinance, you have 100 nanograms per liter for 20, and here you have 4.4 nanograms per liter for 24. Here, there's foodstuffs, especially fish. There's data for fish here, 24 PFAS as P4 equivalents. So different types of thresholds apply under different regulations. And we'll have a look at how these threshold values came into existence. These are based on what's called the relative potency approach. So the idea is that you come up with some concentration, these 4.4 nanograms per liter, that cover 24 PFASs, but not a random concentration of each of them, but the concentration is aligned with the toxicity of each of these substances. Now you need to agree on which substance you take as a reference to come up with a factor, basically, and you need to decide on which effect you want to base this on. Do you take immunotoxicity? Do you take fish toxicity? Whatever. This was for human health. So what the extrapolation was based on was rat liver toxicity, because usually human toxicity assessment is based on mammalian model organisms. So rat liver toxicity, this was the most data rich, but they had to extrapolate for 6 substances. And P4, the most data rich, was set as reference substance. And this is the list of relative potency factors that you end up with. And I highlighted those 4 that are part of the EFSA definition. And for immunotox, they assumed equipotency, right? Here for liver tox, it becomes evident that this is absolutely not the case. So PFNA, for example, has 10 times the potency of P4 in rat liver toxicity. And as of now, we have no idea how well immunotox in humans correlate with liver tox in rats. And our idea about how this correlates with fish toxicity is even smaller. We don't know anything about it. So it's really difficult at this point of time to assess whether a value that was based on human toxicity assessment will be protective for water organisms. And this was a task that Mara and I recently had to try to come up with a recommendation. And I'll try to discuss this in a bit. Why we are concerned about this is the data that's currently available for PFAS aquatic toxicity. It's not a lot. So this is acute data for 6 PFASs and 4 for chronic long-time exposure. This is really not a lot compared to the PFASs that are on the market. And what you can also see, this is milligrams per liter, so compared to deltamethrin, rather high concentrations. And you see quite some spread, especially in the chronic toxicity. So there's some evidence or indication that there's different mechanisms of action in these different organisms. Now, if you compare these data to PFOA, so do the same thing with as with red liver toxicity, which you see here as blue dots. This is the corresponding relative potency in red liver toxicity. You see that the potency of these substances is much higher in aquatic organisms than in red, basically. Meaning that for these organisms, we can't be sure that a value based on human toxicity or red toxicity will be protective of our aquatic organisms. As I said, the question was, can we infer whether this will be a protective value that the EU came up with? We have calculated the risks of several substances that have been measured in Switzerland and compared them for water and for fish. And you can see here, if you compare PFNA, which has factor 10, with PFOS that has factor 2, that the risks for PFOS are still higher for PFNA on average, also in fish. So this means that most probably in most sites in Switzerland, this value will be protective. But there is exceptions. You know Greifensee very well, most of you, I suppose. Data was also generated for this outlet here, River Glatt. This is the outcome of the risk quotients for these different substances. And here you see that PFNA contributes to the overall risk substantially more than PFOS. So this will be a site where the 4.4 nanograms per liter value will most probably not be protective. So at the moment, it's difficult to suggest a value for all sites, basically. And just one last slide on this, just to pick up the topic of TFA, trifluoroacetic acid. We also asked ourselves how will we deal with TFA in our watercourses in the future, because it's not part of the 24 PFASs under the Water Framework Directive. At the moment, we only have 5 effect concentrations that we can use to assess its toxicity. It's not a lot. 5 for all types of aquatic organisms. And we're suggesting that based off of these, a value of 12 micrograms per liter will potentially be protective. We have measured concentrations of up to 1.8 micrograms per liter at the moment. But as we all know, this substance will most probably exponentially increase in its concentrations in the environment. And I'd briefly like to cite a paper by Hans Arp from last year, and Martin was also involved in this, that says that we have good indications that TFA meets planetary boundary conditions. And my last slide on PFAS is this one. All of this means that communicating about PFAS is a real challenge. And out there's the general public and the decision makers that we need to provide useful information to. Personally, I find this a challenge, and it will continue to be one. We've tried to work on this in 2 different workshops with stakeholders that we co-organized with SCART, where we try to get people together and see where the challenges are and sort of agree on ways or find ways on how to phrase our information clearly. And I'm grateful that we were able to do this, but it's a continuous journey. And I'm also glad that we were able to initiate the PFAS expert group, which is a joint endeavor of EMPA, Eawag, and Ecotox Center, where we also try to compile information and make it available to the public, which is to be coming soon. Now, I hope you're still in the mood for a last topic before I close. It's about endocrine disruption in surface waters. And this title isn't as catchy as the other ones maybe, but I feel that from the water protection perspective, we are in a certain dilemma. And I'll try to explain why, and also on my last slide show or propose a solution that we've published last year, I think, but which is not part of any guidance also, but let's see. Now, history again. This time 70 years. In 1938, a chemist discovered that substances other than hormones can have similar effects. They could, in this case, mimic estrogen. Then you've probably heard about the Wingspread conference back in 91, where the term endocrine disruptor was termed. But then it took 8 more years till in the EU strategy for endocrine disruption was coined, basically. And then till 2009, till substances that had endocrine disrupting properties were banned for the first time under the Plant Protection Product Ordinance Directive and the biocides regulation here. So we're talking again several decades till this trickled down into regulation. And to explain the dilemma, oh wait, that's the next slide, I'm sorry. So looking at this from the water protection side, so the Water Framework Directive does mention endocrine-related functions in its text, but the guideline that we work with to establish thresholds does not give any guidance on how to consider endocrine disruption. And our water protection ordinance doesn't go into detail on mechanisms of action at all. And a recent analysis that we did of 180 EQS derivations showed that over 70% of substances that had evidence of endocrine disruption were not treated as such. So this was not part of the derivation process. To discuss this in a bit more detail, I brought one example that's pretty old. It's tributyl tin, which is known nowadays widely as an endocrine disruptor, and for that reason also has been banned in many countries worldwide. It also relates to One Health because it's effective in invertebrates and vertebrates. It's disruptive in humans as well as in mollusks and amphibians. What it does is it has obesogenic effects. It has reproductive and developmental toxicity and neuroendocrine disruption. So a very good example for what we want to have a look at. What you need to do to understand whether something is an endocrine disruptor is you need to create a line of evidence that this is really happening. So what you start with is your primary molecular initiating event that tells you something is happening on the molecular level, but you also need to make sure that there's actual toxic effects happening. So something that translates to the organism and then later to the population. And for tributyl tin, there's a very good review by Laurent Lagardic from 2017 that has established this for tributyl tin, looking at the molecular pathways and the apical outcomes. So for this substance, this seems to be very well established for at least some organisms, but for the most part, we don't have this type of information. Now, sorry, I apparently didn't check all the animations correctly. So our main question is whether the tested concentrations are low enough in our tox assays, and I'll try to show why. In this graph, I've compared delta methrin, which you've already seen, the spread of acute data and the spread of chronic data with tributyltin. And at first glance, you may think this is very similar. Why would we care about tributyltin more than delta methrin? Now, what delta methrin does is, if you look at the dose that you expose an animal to, and you look at the response it shows, so Hyalella azteca, for example, toxicity. For a certain dose, you don't see anything, and then you have a ideally sigmoidal increase and then a plateau right here. Tributyltin does this, right? So you start off with a strong effect, then you increase your dose, nothing happens, and then another type of toxicity kicks in and you increase your effect again. So when you collect your toxicity data here, these points, it could well be that you're on this side of the curve and you think this is a nice dose response curve, but you're missing out on this part. So it's really hard to know whether you've actually tested low enough, right? Now, to summarize this, what we need to do is we need to set a threshold even though we don't know whether we've tested low enough. Low concentrations mean that this is a real challenge for analytics. So if we set a value that's below detection limits, we have an issue with regulation, right? How can we enforce a value that's below detection limit? And if we say we don't want any detection at all, then this depends on your analytical capacities. Now, the solution one is try to do this with bioassays. So instead of chemical analytics, you use a biological indicator that responds at lower concentrations. And our group of aquatic toxicology works on this. And this this concept has, for the first time, been taken up into the Water Framework Directive, which is not yet in force, but at least it's in the proposal. And then, as promised, the second solution, please don't try to understand this graph. It's just a symbol for, symbolic of what we've tried to suggest. Solution two is to apply the precautionary principle, basically, to endocrine disruptive chemicals or those that where there's some indication of this mode of action, is that in EQS derivation, we do a systematic assessment of the scientific evidence for endocrine disruption, which is currently not the case. Then we would suggest to use additional assessment factors to allow for this uncertainty, or to take into account this uncertainty of not knowing whether we've tested low enough, basically. And we've also come up with a decision tree, which is this graph right here, to try to guide the risk assessors through this process and suggesting additional assessment factors. Now, I'd like to close the input part, basically, of what I wanted to present. I've brought some few conclusions, personal ones, which are mainly that I think, looking back in history, we've come a long way, but I still think that we absolutely need to do better. Looking at the complexity, the mixtures that we've created in the environment, the blind spots that we still have, and the fact that we analyze new substances at the moment in much more detail than older ones. We have a huge lack. We lag behind assessments a lot. And what I think, and this is, I'm not the first person to say this, of course, is we need to make data publicly available, have a common database. We need to do one assessment per substance instead of doing this silo type work. And also we need to do aggregate exposure, absolutely, not to look into one exposure route at all. And I think what's very important to me is that we should have a discussion in society on which substances we really want to use for which purpose at which cost. This is something what we are not doing at the moment, I think. And with that, I would like to thank many of you related to what I showed today, the park team that is listed there, the colleagues I collaborated with on the endocrine disruption proposal here, Lothar, who's a great collaborator on many topics regarding human toxicity and workshops we've organized. The PFAS group newly formed at Eawag Ecotox Center, the Ecotox department, everyone there, the biofilm crew, and of course, Ecotox Center, for being such wonderful colleagues, supportive. And as you're here, Marion, I also want to warmly thank you for your guidance and your support.